All right, so my name is Grayson Gilbert. My teammate is Marcus Hurt, and this is our ENPM 700 final project. So it's called Project Mars, and Mars stands for Multi-Agent Robotic Slam. So next slide. So right now we have the high-level agenda. So first we'll kind of cover the project overview. Then we'll go into what went right with the project and things that we're proud of. Next, we'll cover what went wrong and some of the many challenges that we faced. And then finally, we'll wrap up with a project demo. So next slide. So project overview. So the project overview is, well, first Mars. So multi-agent robotic slam. So that's the overall goal of the project, and it's going to be a ROS2 project that supports a scalable architecture for multi-robot slam. So we really wanted to, facilitate rapid mapping of large unknown facilities by using multiple robots at one time that can then combine their local slams into one global map. This project will leverage Slam Toolbox, Nav2, RViz, Weebots because we don't have the actual hardware on hand, Turtlebot 3, and then everything was developed in C++, with the exception for our launch files, which are in Python and YAML. As far as the general process, we're going to have individual robots that are navigating around unknown spaces, each creating their own local 2D maps of where they've traveled. And then this map will be shared with that central overseer node, which then combines all the local maps into one global map of the facility. So next slide.
So I'll jump in here and just take us through a high-level architecture. So kind of like Grayson was saying, we've got this overseer node that subscribes to each robot's map and toolframe topics and publishes a global map. And then each robot is running its own SLAM and Nav2 stack, and they create their local SLAM map and publish it. And they subscribe to the global map for future development, possibly using the global map to update our local maps. And then you can see on the right our repository architecture. The high-level architecture is just the Culcon workspace is Project Mars, and then inside our source we've got three packages. We've got the Overseer, which does the global map merging. We've got the Mars Exploration package, which is a robot factory. So each robot has its full frontier algorithm, and local frontier algorithm, and a Nav2 and Slam stack that are brought up through the Mars Exploration package. And then we have the Fleet Bring Up package, which is it launches the Overseer, each of the robot Mars Exploration nodes, and Weebots and RViz for visualization. So that's the high level of our repository.
So diving into the activity diagram, we'll kind of move from left to right. So the project and simulation starts with the Mars Fleet Bring Up package. We're going to launch the simulation, and it will then spawn X number of robots with their own namespaces. And then after everything gets spawned and started, the Mars Exploration package will take over and perform local frontier exploration with each robot of a global space. So each one of those robots are then going to complete their own local SLAM and generate local maps, which are then published to the map topic within their local robot namespace. Then the Mars Overseer node subscribes to those map topics of each individual robot and then merges all the local maps into one unified global map and publishes that to the global map topic. So now that's kind of like a high level overview of what goes on throughout the project. Now we can kind of talk about what went right and things that we are generally proud of from the project. So one of the things that we are proud of for this project was the test-driven development approach for both the final project as well as the midterm. We thought that the test-driven development approach in the overall was a net positive. So it definitely slowed down our development in the early stages of the project. But, long term, it was successful because it allowed for collaborative development. And it also allowed for kind of easy integration of different packages to be kind of worked independently and then integrated together. So one of the challenges about this test-driven development approach, though, was that it definitely can be difficult to write tests for software when you're also learning the concept at the same time. But that was something that we overcame throughout this project. So another thing that we're proud of was the detailed project planning for phase 0 and phase 1. So definitely we found that creating detailed plans of the project from the very beginning stages improved our overall approach and architecture of the project. And long term, as we progress throughout the stages of this project, being able to lean on that the initial planning stages really helped. Another thing is going to be branching in Git. So, keeping our working branches and feature branches separate throughout this development process really allowed for each driver to have a clean separation of work, and it made the overall merging process when we were done with a phase much smoother. And then one other thing to note was the use of our factory design pattern in the Mars exploration package. We are able to spawn any number of robots using that same factory, which was an efficient way to structure that project, even though we are limited via the computer hardware when we're actually running the simulations. So that kind of covers the main, what went right about our project. And now Marcus is going to discuss some of the challenges that we face later on in phase 2. So.
Yeah, so what went wrong? Some of the things that we would want to highlight, although there were plenty of things that went wrong, would be the frames and namespacing. So we use the SLAM toolbox and the nav2 stack to control our robot and do our SLAM mapping. And those are extremely useful tools. When we were doing single robot tests, that's super successful in phase 1. But when we got to phase 2 and we started trying to do a second robot in the world, we ran into this bug, which is actually a known bug that we hadn't discovered until we got to phase 2, where the Turtlebot LDS01 sensors, they have their frame ID hard-coded. And the Turtlebot project knows that this is an issue. And so they have a newer LDS02 sensor that actually fixes it. But the problem is Weebots currently only supports the LDS01 sensor. So we had to overcome that by basically modifying the things that were being published from LDS01 so that we could use them in a namespaced nature. And similar to LDS01, all of the nav2 nodes that we launch through our launch file, they also need to be namespaced. And if you're working in ROS2 with launch files, the namespacing of topics is pretty clean and it works very well. We didn't have too many issues with that. But tool frames need to be manually rewritten because they don't just automatically prefix with the namespace, which can be an issue. So that took a little time for us to overcome. And in addition to those two, we also had an issue with the nav2 stack, which was kind of an oversight in our proposal. So we're using nav2 so we pick a point in the map and nav2 generates a path to get to that point. We anticipated that being the simplest way to choose a frontier algorithm. That way we could just pick points that made logical sense and nav2 would handle the path calculations for us. The problem with that is creating a frontier algorithm is a little harder than one would think. At first we thought, well, we'll just pick, a close free node. That's great, but what if your close free node is on the other side of a wall? Or what if your close free node doesn't give you enough new data to improve your SLAM map? So we had to develop some improvements to our frontier selection. And then the final issue that I want to highlight is just scaling to 3 robots. Along with all the namespacing issues we ran into, uh, our hardware had some trouble keeping up. Running Slam plus a Nav2 stack plus Weebots, and each robot has its own Slam and Nav2 stack. Your CPU starts to hurt. So we were only able to get on our hardware 2 robots running. Once we tried to add that third one in, just we couldn't get anywhere near to real time. Um, and that's a good jump into the last thing for our presentation, which is the project demo. Hello, everyone. My name is Marcus Hurt, and I'm going to be taking us through a quick single and 2 robot demo for our Project Mars. So here you can see me launching our project. This is going to be the single robot demo. So you can see our single Weebot in the corner. It's a turtle bot. And then you can see our map being generated here on the left. So this is single robot slam. So it's going to be a little slow. We're just going to drive around here and map a little portion of this space. I'm just aligning the space with the slam maps so that it's easier for us to see. So you see that back corner, it's getting aligned well. Our overseer is actually still in charge of picking up these maps and merging them. So what you're going to see is as new maps get published, the gray areas are lower confidence areas that are slowly overridden by newer and newer maps. So you can see us mapping the left side of this room here. We're just picking frontier nodes, which are nodes that are not yet explored in the local map, and driving to them. And then we publish the SLAM update, and the overseer merges that with our current global map. So that's the basics of single robot SLAM. Let's hop over to our 2 robot SLAM demos. And as you can see, our overseer is broadcasting the global map with each of them realigned to the global map's coordinate reference. So they're both going to drive around a little bit. This is a little bit longer of a demo than the first one, but see, this robot just got some updated SLAM maps. Now the left robot has some updated SLAM maps. And you can see they're not perfectly aligned, but they are doing a pretty good job right now of aligning to each other. So, and the overseer consumes that and just goes ahead and stitches them together so that you can map a large factory floor as fast as possible with as many robots as your hardware can handle. Our hardware can only handle 2 robots at a time. And even then, you can see my sim time here. The previous one, we stayed pretty close to 1x. Definitely a lot better than this one. This one, we dropped down, a tenth of real time sometimes. And it does run better when we're not recording at the same time. So unfortunately, in order to capture this video, um, we we did lose some simulation time. But yeah, so these robots they're both running full SLAM and Nav2 stacks and doing frontier exploration. So feel free to download our package and try it yourself. See how many robots you can get to run. Best of luck getting past 3 because ours did not want to do more than 2. So, all right, thanks everyone.